Hello and welcome to another Piper Pod. Today we're going to focus on respiratory physiology. Today's lesson I'll go into the starting point of respiratory physiology, but from there you keep reading a lot. There's a lot of science, there's a lot of interesting reads to do with gaseous exchange, partial pressures, ventilation support, all that sort of stuff that you can go on to and increase your understanding on this. So like I said, this will be mostly an introductory level to some of those areas and hopefully give you a better understanding of how respiratory physiology works. So the overall function of respiratory physiology is broken down into 4 aspects. Now 2 of those aspects are controlled by the lungs themselves. The other 2 are a combination of the blood and the tissues themselves. So pulmonary ventilation is referring to just breathing, air coming in, air going out. External respiration is the gaseous exchange at the airway to the capillaries. Transport is the movement of gases around the body, and internal respiration is the swapping of gases from the capillaries into the tissues themselves. So before we start talking about ventilation, we need to understand a few concepts. Okay, now we're just going to mention quickly one of the gas laws. Okay, so Boyle's law plays the biggest role in normal breathing and what drives air movement, if you will, within our body. So Boyle's law basically says that the gas pressure in a closed container is inversely proportional to the volume of the container. Okay. So pressure differences and airflow is actually what we're talking about when we're dealing with Boyle's law. So what it means in a nutshell is if you have the same volume of air inside a container, then it's going to fill that entire container and it's going to push against the walls, and depending how much air is in that container will determine the pressure. If that container grows larger with the same amount of volume of air in it, then once again the gas is going to fill that space, but the distance between the molecules is going to be greater, therefore the pressure exerted on the walls of the container are going to be less. And that essentially is how pulmonary ventilation works. It's a mixture between atmospheric, intrapleural and intrapulmonary pressures. So atmospheric pressure, generally speaking, is around 760 millimeters of mercury. Okay, so that's your atmospheric pressure. Like I said, all this is quite generally speaking. We can't account for all areas, but this is just to make it easy. Now, intrapleural pressure, that changes as we breathe, but it always has to be negative compared to the atmospheric pressure, because if it wasn't negative, when we get positive intrapleural pressure, that's when we start getting the lungs collapse. So when we have a pneumothorax, it's a direct result of positive, compared to atmospheric, positive intrapleural pressure. Right, now, intrapulmonary pressure, that obviously varies the most as we go along, because it is the variation in intrapulmonary pressure that causes our inspiration and expiration. So firstly, let's look at inspiration, how air gets into our body basically. So when we're at rest, our atmospheric pressure and alveolar pressure is equal. So therefore there's no movement, no in and out, nothing happening at all. When we increase the volume of our thoracic cavity, then obviously we create a negative pressure within our alveoli themselves. So the pressure drops to 758 millimeters of mercury. Okay, and that obviously creates a negative pressure compared to atmospheric pressure that was around the 760. So it draws air into the lungs. Now obviously the way that our chest cavities expand is our diaphragm contracts down and our intercostal muscles contract out. Now we'll talk a little bit later about other things that control it, but that's essentially it. So when we create this greater space, the air that is within our lungs obviously moves out to fill that space, creating a greater distance between the molecules, and then from there the pressure that exudes on the walls is reduced, so air comes in to equal out the actual pressure itself again to fill that new space. when we finish inspiration, we obviously hold air in there, and obviously there's no movement in or out, okay, because it's now equal. You still have equal atmospheric to alveoli pressure, just with a much larger capacity within your thorax. So then when we move into expiration and everything starts to decrease in size, then we have the opposite effect. Now, the thing that needs to be really carefully noted is that with normal breathing, normal in and out, relaxed breathing, there is no contractions at all during expiration. So all that happens is the diaphragm and the intercostal muscles are connected to stretch fibers, and those stretch fibers move back into place. So your chest cavity moves back into a resting place. But whilst that's happening, the alveoli pressure increases to around 763 millimeters of mercury, which is greater than atmospheric pressure of 760. So air is forced out of our lungs, just like that. So it's just the changes in pressure that causes air to come in and air to go out. And that is pulmonary ventilation itself. Okay, now there's certain things that can influence the airflow as the amount of air that comes in. So obviously the size of your airway plays a huge role in that. So the more diameter there is in your airway, the more air that can actually come in a certain time frame. So in better contrast is if the airways are small, like in bronchiolitis or bronchiolitis, asthma, COPD, any of those, essentially your airways become smaller. Okay, so when they become smaller, you're only able to have a certain amount of air physically that can get through in order to fill the airspace within a certain time frame. On top of that, there's also conditions like atelectasis that causes like a bronchi plug in there that it blocks off the alveoli sacs and they cause it to collapse. Now, sympathetic and parasympathetic nervous system play a control in the amount of air that comes in. So obviously sympathetic will cause your bronchodilation, therefore getting more air in, increasing your thoracic capacity, that sort of thing, whereas parasympathetic will do the opposite, reduce that side of the house. Surface tension is probably the main one that assists us in maintaining the internal pressure or the internal volume of our alveoli. So surfactant essentially will line the surface of the alveoli produced by specialized pulmonary cells, and from there it will decrease the overall surface tension that we find in the alveoli sac. And what that prevents from happening is the alveoli collapsing and then sticking together. So by having that decrease in surface tension made by the surfactant will actually aid in keeping the alveoli open and therefore allowing more air to come into the actual lungs themselves. Okay, so there's some factors that will influence how much air flows into our lungs on any given time. Alright, so speaking of our lungs, we'll have a look at certain capacities that we have. So we have a normal capacity, which is called tidal volume. Now that's essentially what comes in and out. Easy to remember because it's associated with the tide. So normal breathing in and out is around 500 mils. Now if you want to get technical, it's about 7 to 10 mils per kilo of body weight is how much your tidal volume is. So we'll just say 500 mils for ease, and that's your normal breathing. If anything happens and you need to increase the amount of air you bring in, then that is inspiratory reserve volume, and that sits around 3 litres, making an inspiratory capacity. Now, the other side of the house, you have an expiratory capacity. So on top of the tidal volume coming in and out, you can also force about 1 litre extra air out of the lungs, basically leaving just residual volume. This is what happens when you breathe out everything you can, and then all that's left is the residual volume itself, and that will give you a functional residual capacity. So this is what is left in your lungs normally after you breathe in and out tidal volume, okay? And that's quite important in maintaining a certain pressure within your lungs and also maintaining certain concentrations of gases as well. Now your vital capacity is everything that can move in and out of the lungs. So it's your inspiratory, expiratory reserve volume and your tidal volume. all put together. So that's how much air you can move in and out of your lungs compared to total lung capacity, which is that number plus your residual volume. Now, when all this is happening, the tidal volume represents the amount of air that actually can transfer to the alveoli to be put into the bloodstream, minus what's known as dead air volume. Okay, so that essentially means all the air that fills up the bronchioles and the bronchi themselves is dead air volume, and that's about 150 mils. When we're breathing for somebody and we have a good interthoracic pressure, we don't need to squeeze too much on that BVM. Okay, you just need a little bit each time in order to replace what's known as that tidal volume itself. Okay, so that's your normal breathing, and then obviously we can increase or decrease either way, depending if we suck air in to max capacity or breathe out to max capacity. Now, from there, there's obviously a few other things that happen besides our normal breathing in and out that control air movement. Okay, so coughing and sneezing is a reflex response designed to clear out the upper airway or the lower airway. So sneezing is designed purely for getting rid of what's there in the upper airway, and coughing is to help bring up what's at the base of your airway. Now, crying and laughing actually take over your breathing patterns, as to will hiccups. Hiccups are controlled by diaphragmatic spasms, whereas laughing and crying will essentially make you take a whole bunch of short, sharp little breaths, which is not really normal breathing. Now, yawning is a bit of one of those ones that they research quite a bit, and essentially what they look at doing is your deepest inspiration, and the idea is it wants to fill every alveoli. Okay, so that's when you yawn, is every alveoli is filled to its capacity. Okay, so that's basically the ones that will control our non-normal breathing air movements within our body. Okay, once the air gets into our lungs, we need to figure out what happens to it there. So the body has the ability to shunt and increase the amount of assistance, if you will, that can aid in going from airflow to blood flow. Okay, so the pulmonary vessels can constrict, okay, in the areas where the oxygen flow is too low. Okay, so if you're not going to pick up much oxygen from an area, it can constrict that area off and then have more dilation around the areas that actually has higher concentrations of oxygen present. Remember I just said as yawn fills all the alveoli? So for normal breathing, the alveoli that aren't full, pulmonary vessels aren't going to waste blood on that area, so they can shunt it from there to go to another one. Now, the same thing can happen when we need more air to come in, or we need more oxygen to come out, or carbon dioxide to come out, is our airways can get larger, therefore allowing a greater passageway of air to come in, and sometimes more importantly, a larger capacity of carbon dioxide to come out. Once the air gets into our lungs, it needs to swap over into our bloodstream, and this again is all about pressures. Okay, not atmospheric or pressure like that. Now we're talking about partial pressures. So each gas within our atmosphere will contribute to a overall atmospheric pressure. Now each one of those individually are denoted as a partial pressure, which is what you'll see represented as a P. Now a lot of gases can dissolve into liquid. Okay, so a lot of the gases that we breathe in will dissolve into the liquid, some more than others, and essentially the amount that dissolves into the liquid will be determined by the partial pressure that's coming in. Now when we look at O2 and CO2 exchange, we are dealing with diffusion only. Okay, so it's basically only moves with their concentration gradients. So from a high concentration to a low concentration is the only way that O2 and CO2 can move. Okay, as you can tell, they don't have an ionic charge. Okay, so they're not controlled by any form of ionizing opposing forces. It is just a gradient of their concentration gradient curves. That's all that controls the movements of gases. Okay, so if we look at oxygen for starters, we all know that oxygen makes up about 21% of the atmosphere. Okay, so if we say the atmosphere is 760 millimeters of mercury pressure, now obviously that changes, we know, but just say it is, and then we figure out the 21%, it actually gives us 160 millimeters of mercury partial pressure O2 in the atmosphere itself. Now when we breathe that in, it mixes with the concentration that's already in our lungs, that residual volume, plus or minus the actual expiratory force volume, and then we get a mixture concentration of around 105 millimeters of mercury. That's what we'll find in the lungs themselves when we breathe in, is 105 millimeters of mercury of partial pressure oxygen. CO2, on the other hand, represents a very small percentage of the atmosphere itself. So if we were to figure that out, then it's 0.3 millimeters of mercury of partial pressure of CO2 is what we find in the atmosphere. When we breathe that into our lungs, the residual CO2 volume that's already left in our lungs gives us a partial pressure of 40 millimeters of mercury found in the alveoli themselves. Okay, so that's the numbers that we're dealing with. Obviously, anything that knows anything about the atmosphere and altitude and temperatures and gas laws know that these numbers vary. But for the purpose of this particular presentation, you're just learning gradient curves of oxygen versus carbon dioxide and why they tend to move throughout the body. That's all it is. Okay, so once we get to the alveoli itself, if we zoom in on the top picture, that just represents a alveoli sac. Now, as mentioned, we have special pneumocytes that create our surfactant that helps keep our alveoli open. We also have macrophages within our alveoli that can help destroy any foreign bodies. This is where the partial pressures of gases will come to, and then they'll diffuse through the membrane, so through the surfactant, through the membrane, through the interstitial space, through another membrane, before they finally get into the actual red blood cell themselves. Okay, so they've actually got quite a few layers to diffuse through. Luckily, they're gases and they can move through quite easily. They don't have to have special ion channels or anything like that. They have the ability to pass straight through these membranes into the bloodstream based purely on the amount of pressure associated with either side. So looking at that pressure, we've already established that what's coming into the lungs is 105 and 40. Now I told you things change, so this particular one here says 100. Let's try not to get bent around the axles pretty much, okay? So when we have deoxygenated blood coming in, the deoxygenated blood will have a partial pressure of O2 of 40 and a partial pressure of CO2 of 45. That's what's coming in. So when it meets the respiratory membrane, we have a whole bunch of oxygen coming in because of the partial pressure, and then a whole bunch of CO2 flowing out. End result wants to be is you want to have equal gradients of oxygen and CO2 in the alveoli and in the capillary itself as it's moving out. So as you can imagine, there's a lot of conditions and there's a lot of physiological effects that can alter the amount of oxygen that is coming in and through the amount of CO2 that is going out into the body. And we might talk about a few as we go along, but that's what external respiration wants to occur. It wants to have an equal concentration of gases on the alveoli compared to the pulmonary capillaries themselves. And it does that through diffusion of concentration gradients. Okay. From there, the gas is now in the bloodstream and it needs to be able to be transported around to the rest of the body. So oxygen, we know, is transported in the blood, and we also know that most of it is bound to hemoglobin. Okay, so 98.5% of oxygen that comes in will bind to hemoglobin itself. Now it binds to the heme group of each hemoglobin, and each hemoglobin can carry 4 oxygen molecules, and each red blood cell has thousands and thousands and thousands of hemoglobin. So you've got a lot of capacity to carry your actual oxygen molecule. Now it's the partial pressure of oxygen, which is the most important factor that determines whether or not oxygen is going to bind to hemoglobin and then 2, whether or not the oxygen is going to disassociate with the hemoglobin to go into the tissue themselves. Okay, so it's the partial pressure of oxygen that is the most important factor. Okay, and that brings us up to the O2 hemoglobin dissociation curve, which I know you all have heard about before. But just in case, we're going to go through a bit of normal physiology, and then we'll talk about the concentration curve itself. So when we're breathing, when we're normally at rest, actually happens when we don't need a lot of oxygen, is all your oxygen, 98% of it, traveling with the hemoglobin, will travel around to the tissues, and then 23% odd, 23 to 25% of the oxygen is bound to the hemoglobin, will be released for the tissue. Okay, that's normally what happens at rest. So 1 in 4 of those hemoglobins that are bound, oxygen molecules that are bound to the hemoglobin, will be given to the tissue. The other 3 will stay on the hemoglobin, okay, because most of the time we don't need an increase in oxygen. Okay, most of the time at rest we do not need an increase in oxygen. So that is what happens when we're dealing with normal saturation rates. And the curve is pretty good as long as our O2 saturation stays around 80 and our partial pressure of oxygen stays around 40. We're still going to be able to get this normal transfer of oxygen. Now, if for some reason your partial pressure of oxygen decreases, what that means is it will not have enough pressure within itself in order to transfer to the tissue. And be able to pick up a lot, as long as there's enough oxygen coming in at the lungs, it'll be able to refill itself. But by the time it gets to the other end, so to speak, to the tissues, if it's not at least 40, you're going to have a pretty decrease in the dissociation of oxygen transferring over. So that's why when we're dealing with oxygen saturations, we say 93, we want to keep it up. Okay? And when we get to 80%, you have a massive decline in the person's vital signs. Okay? It's because of the ability for partial pressures to transfer over. So what basically happens is if your partial pressure is too low, then your hemoglobin's going to hold on to it. It's not going to pass it over to the tissues, okay, because there isn't enough pressure associated with that transfer. Okay, so this sort of thing happens when you have decrease in blood flow, or decrease in oxygenated blood getting to areas, shock where everything gets reserved back into it, not getting enough oxygen in the body. Your body will actually hold on to it. Remember, it works on diffusion. So it's not going to pass anything over if the partial pressure of oxygen isn't that great. So we need enough partial pressure of oxygen at the tissues in order to elicit a transfer of oxygen to those tissues. Okay, and that is basically as simple as it does. From 80%, you have a massive decline in vital signs. Now, on top of that, the gas transfer mostly of O2 plays a huge role in maintaining our pH, CO2 and temperature as well. So if you look at the curve, as our partial pressure begins to decrease, so here we are, we're looking at a partial, in A, we're looking at a partial pressure of oxygen of less than 20, which gives us an oxygen saturation of around 30. Okay, so that's pretty bad. Okay, all right. When that happens, obviously we get a increase in CO2 for partial pressure, which decreases our pH and causes our temperature to rise. Okay, that's basically the physiological effects of not getting enough oxygen to the tissues. Now, if we increase the amount of oxygen coming into the lungs, then the hemoglobin can be refilled up to a partial pressure of over 100 millimeters of mercury. Now, you can actually get partial pressures much higher than 100 itself. Okay, we can't get oxygen saturations any higher than 100, but partial pressures we can. And that's what oxygen saturation achieves, positive pressure ventilation, all that sort of stuff increases the amount of PO2 and technically FiO2, but we'll get onto that maybe another day. It increases the amount of availability in the body. Now from there, it decreases the CO2, which in turn increases our pH and decreases our temperature. So it keeps us more in a homeostatic base itself. Okay, so the decrease in oxygen, we all knew that it was bad, but you should remember that you have a rapid decline based purely on the partial pressures that are found within our body, and then ongoing effects with our acidosis status and temperature statuses as well. Okay, so that's oxygen and the roles it plays in our body. So let's have a look at CO2. So when CO2 comes into the body, about 7 to 10% is transported in the plasma itself. Okay, 23% binds to the globulin aspect of hemoglobin, but 70% of it, give or take, actually is transported around in the plasma as bicarbonate. Okay, and it's actually made into bicarbonate in the red blood cells. So let's have a look at how that occurs. Okay, so when CO2 comes into the body, it binds with water. Now, there's plenty of water in the blood. Okay, it's made up of the plasma, and that gives us a compound called carbonic acid. Now, this process can happen in the plasma, but it takes just too long. So the actual red blood cells take care of this itself. So carbonic acid dissociates as a hydrogen ion and bicarbonate itself. Now, when we swapping over to bicarbonate, it's just a matter of shifting a chloride molecule out in order to balance the ionization, and then we're fine. All of a sudden we have free-flowing hydrogen and bicarbonate in our body, which really is CO2 and water floating around our bloodstream. Okay, but it gives us a massive advantage because we have the bicarbonate there. It can actually work as an additional acid buffer itself. So let's have a look at see how that works. So when we get CO2 produced by the tissues, as it always happens, we looked at it in the metabolic function. As soon as we go into cellular metabolism and we start looking at the Krebs cycle, then we start producing CO2. Okay, easy done. So CO2 is produced, moves into the bloodstream because of partial pressures. It's much greater in the tissue compared to the partial pressure found in the blood, so it moves over. It binds to water and becomes carbonic acid. Then carbonic acid is broken down and it becomes a bicarbonate and a hydrogen ion. Hydrogen will bind to the hemoglobin, so then we don't actually have any free-flowing hydrogen ions at this stage. So everything's safe. I know you're all thinking, if you have all this free-flowing hydrogen ions, how can this whole system work as a buffer for acidosis itself? Well, that is your answer. It binds to the hemoglobin as it goes. Now, when the blood comes to another area of change of partial pressures, so now we have the ability situation where we have an increased CO2 partial pressure inside the capillary wall compared to what's found in the alveoli, then the exact opposite occurs. So hydrogen ion breaks from the hemoglobin, binds with the bicarbonate, becomes carbonic acid, we put back our chloride molecule, and then it gets turned into water, which stays in the red blood cell itself, and CO2, which is transferred through the lung. Now, this happens in the red blood cells with the help of an enzymes, which is our carbonic anhydrase itself. So like I said, it can happen by chance in the plasma, but it's expedited in the red blood cells, and that process is how most of our CO2 transfers around. And that process itself is also what helps us aid us in providing a buffer for acidosis in that normal range of 7.35 to 7.45, just by swapping free-flowing hydrogen ions that are produced by soaking it up with the hemoglobin and putting it onto the bicarbonate, making carbonic acid. And that's basically how the acid buffing systems work, but we'll probably talk about that in future lessons. Okay, so just to go over pretty much everything we talked about the 4 levels of respiration. Okay, so we have pulmonary ventilation, which is the air coming in. Now, as we've already established, the air has partial pressure of 160 oxygen and 0.3 carbon dioxide. But when it comes into the alveoli and is mixed with our residual, then we get 104, 105 oxygen and a 40 CO2. Okay? When the deoxygenated blood comes to the lungs, then they swap and they want to equalize. So then what goes out becomes a partial pressure in the blood flow, the equivalent to what you'll find in the actual expired air side of the house. So I just want everyone to take note here that it's actually the inspiration side of the house that dumps off CO2, not the expiration side of the house. The expiration obviously blows it into the atmosphere, but the swapping at the external ventilation area happens during inspiration, not expiration. Right. Once the now oxygenated blood travels around the body, it gets to the tissue. Okay, now obviously a few of it is utilized on the way with the heart, the brain, all those vital areas take up a little bit of the O2, which means by the time you get to the tissue, the capillaries, we still have a large partial pressure of oxygen compared to what we find in the tissue, and in the tissue has a larger CO2 compared to what we find in the blood. So the opposite occurs. This is internal respiration. Okay, so once that swapping occurs at the cells and the capillaries, then it travels back around to the lungs in order to be reoxygenated, carbonized, and then the process just continues. As you can see, it's all done because of partial pressure gradients, and that's it. Okay, so let's look at what controls our breathing mechanisms. Okay, so we now know what respiration is all about. Let's look at the things that control what actually allows us to breathe. So there's 3 control centers in the brain that help us breathe. Now the main one in our resting everyday side of the house is our ventral respiratory center, which is part of the medullary respiratory center itself. So we have 2 respiratory centers in the medulla and 1 in the pons. The main one is the ventral respiratory group, and that will just send messages to the actual to the phrenic nerve, to the intercostals, and they will just breathe themselves. Inspiration and then recall elasticity. Inspiration, recall elasticity, and you'll just breathe normally. Okay, the dorsal aspect is what connects to our chemoreceptors around our body, and from triggers from them, which we'll talk about next, will actually cause an increase in respiration, but also can cause an actual positive effect on the internal intercostal muscles themselves. So basically when we breathe in, we obviously just have an increase of our diaphragm and our intercostal muscles, and most of the time nothing happens. When we physically want to breathe out or increase effort, then our internal intercostal muscles can kick in, which essentially will cause an increase in that contractility. Okay, now the dorsal ventral root is also responsible for kicking in accessory muscles. So for inspiration, we get our sternocleidomastoids, our pectoral minors will kick in order to increase capacity. And during expiration, we have our internal intercostal muscles and our abdominal muscles that will physically cause pushing on the thoracic cavity to increase that. Okay, now that's controlled by the dorsal respiratory group. Okay, and that's mediated by chemoreceptors. Now the pontine respiratory group augments the ventral group and the dorsal group in times of need, like exercise, sleeping, talking, all that sort of stuff. So essentially takes over and tells the group when to actually breathe during times where it's not chemo related and when it's not just normal resting related. Okay, so that's what your pontine respiratory group will do. It will take over, allow for smooth inspiration and expiration. Whilst I'm talking like this, even with a cold, the pontine respiratory group is working overtime, okay, allowing for that smooth transition through these medullary respiratory centers. Now the chemical mediators for our breathing is arterial PO2, arterial PCO2, and arterial pH. Now because of the reserve that we have in our body of oxygen. As I mentioned, only one quarter is essentially transferred out, meaning three quarters are left in our circulatory volume. Means O2 is a terrible way to regulate ventilation. If it was, then we wouldn't breathe anywhere near as much as we do, and we'd lose most of our reserve. Okay, now CO2 is the most important regulator for ventilations. Okay, now that you increase your ventilation with the smallest amount of increase of partial pressure CO2. Okay, so it will definitely do it. Now, when we have an increase in hydrogen ions, which is usually associated with an increase in CO2, but not solely, then that can also kick in. Now, the reason that that's a secondary effect is if we have an increase in arterial pH as a result, not from CO2. Hydrogen can basically, the acidosis side of the house can cause you to breathe out more CO2, more than usual CO2, as a means of compensation. So it's not a primary center, it's more of a survival chemoreceptor in order to aid in the balancing of your pH. Now these receptors are found in your brain and in your aortic arch of your heart. Now when either one of those are triggered, they will send an impulse to the medulla, in this case, okay, to the dorsal area of the medulla, which will communicate with the ventral, and it will cause the phrenic nerve and intercostal nerve in order to breathe. Okay, now it's obviously the secondary third messages that come from the pons center and the actual the dorsal group itself as well, which will help smooth out or decide whether or not we need to engage our active expiratory muscles as well. Non-neural, as you can imagine, we have a lot of factors involved in breathing. Now, talking and exercise, that obviously increases your breathing. Now, even though it says that it's non-neural control, it's if you really want to get technical, of course it is, okay, because it's taken care of by our pons. Okay, our pons will communicate with the medulla and therefore will actually have neural influence on our breathing. But at least initially, it's taken care of by a lot of other factors, higher functioning factors, compared to just simple neural passing over. Your velation, on the other hand, is completely you. If you want to hold your breath or you want to breathe 60 times a minute, then you can do it. You can bypass every message your brain is telling you, and you can just do it as well. Now, your frontal cortex and your emotions can also play a role in how much you breathe as well. Okay, so pain receptors, your emotional, like crying, being upset, being scared, all can alter the amount that you breathe too. So it's a lot more complex than I've essentially gone through. We have conscious control, emotional control, and physical factors that can influence and take over our normal rhythmic breathing and also bypass our chemoreceptors as well. Right, we'll finish up and we'll just look at some babies. Okay, so if a baby was to be born at 28 weeks, then they should have enough respiratory development in order to breathe on their own. Before that, the lungs are completely filled with fluid, and gaseous exchange is via the placenta itself. Okay, when the baby's born, the fluid shifts, external, internal, doesn't matter, the fluid shifts and the lungs begin to inflate. But this process can take about 2 weeks for the lungs to fully inflate. Okay, most people think it's instant, but it's not. Now, before 28 weeks, the main reason that the respiratory centers aren't viable is because surfactant isn't there. So a lot of the times with premature babies is they'll actually implant this detergent-like substance into the baby's lungs in order to decrease that surface area, stop the lungs collapsing on themselves. Now, when a baby's first born, they're still learning the regulatory controls over their breathing. Obviously, they haven't been doing it for their entire time within the womb, so they will have very erratic breathing patterns. So it will go from 40 to 80, and literally, if you watch a newborn baby breathe, there is no rhythmic cycle to it at all. It's all reflex based, all pressure survival reflex based. Now, by the time they get to infancy, then it starts to get more of a rhythm. Get to about 30, and then it decreases with age until we get to about adults. Adults, and at 12 to 18 breaths per minute. It's mostly got to do with efficiency and the finishing of development as well, is essentially why we breathe a lot less than our little ones. Now, as we get older, our ability to control mucus and surface tension and bronchial dilation decreases, so our breathing effort becomes a lot more, and most of the time, due to our environmental factors, we end up with some form of respiratory disease that just makes it that little bit harder as well. Well, there we go. That is respiratory physiology in a nutshell. I apologise for the cold that I have. Hopefully it didn't affect the voice too much. It's kind of ironic doing respiratory physiology when I can barely breathe myself. But take it for what it is from here. Keep reading a lot into it. There's a lot more to learn, especially when you start moving clinically in line. This is just the physiology within the body. And until next time, take care.